Ready, Leah? Here's the special can full. 3 holes in the side. And why does the water flow out like that? Simple, really. There's more water inside the can pressing on the bottom than on the top. It's that greater pressure that's pushing the bottom stream out farther. Switching to replay. If you dive in the sea, you soon realize that water pressure increases the deeper you go. This girl is collecting starfish that live about 40 feet down, and the pressure she feels is about twice what she feels on the surface. The deeper she goes, the greater the pressure will get until she daren't go further with equipment like this, because the pressure of all that water above her could be dangerous. One of the reasons pressure increases the deeper you go is because you can't squash water. It just won't compress. Here's another interesting thing about all liquids. You'll need some sort of dish, and for this experiment, you've got to weigh things as you go along. That's about 300 grams. Write it down. Now for the glass dish. Pretty heavy, and we're going to need the water. Now fill the dish right to the top. Don't splash any over the sides. You'll see why in a minute. Is it full enough, Piers?
Yeah, I think so.
Okay, Tom, you ready? Now weigh the wooden block. Exactly 200 grams. As you lower it into the water, gently, watch the spring balance. Now all the weight is disappearing, and water has been pushed over the edge into the tray. So that's going to be our next measurement.
About 650 years.
Carefully, out with the glass dish. Remember, the pan on its own weighed 300 grams. The block of wood weighed 200, and look at that, 500 grams. So the water in there is exactly the weight of the wood. So when the wood block floated and seemed to be getting lighter and lighter, it was really pushing its exact weight in water over the side of the dish. It displaced the water, and that's a very important word to remember. Let's prove something really obvious. Heavy things sink in water. Well, nothing surprising in that. We all know it. Your plasticine has dropped right to the bottom, but it doesn't have to. You could make it float. You're right. Flatten it out and make it into a boat shape, like a cup. That's going well. Nearly there. Now back in the water, and what happens? 1, 2, 3, and 4. All floating, even though plasticine is heavier than water. In fact, you can float anything so long as its own weight will displace the same weight of liquid. Now try this experiment. Pour out a glass of cooking oil, and in the other glass you pour some fruit juice. All you need now are those special floats you made, the bits of drinking straw weighted down at one end with a lump of plasticine. Put it in the oil, gently, and mark off the level where it sticks out. Now do the same in the fruit juice. Look how far it's sticking out compared with the oil. Let's do another experiment that'll give you an idea of why that happened. This is easy. Just pour some hot water into a glass. Not too hot, you don't want to crack it. Then drop your float in. Good. Pretty high. Mark the level it floated at. Okay. Now put it in the other glass, the one with the cold water. Mark it carefully. Now, show me the difference. What we've found out is a way of measuring the density of fluids. The denser they are, the less the float sinks into the liquid. Now, let's do some more. Right, this one has taken a bit of preparation. Start off by pouring the inky water mixture into the glass. It's another way to experiment with the density of fluids. Next, some cooking oil. That's it. Gently down the sides so it doesn't splash onto the blue, because you don't want to disturb it. It sits on top. Very good. Now, thick oil from the garage. Not too much of that. Now you see, that sits on top too. And the final thing, some turpentine. Gently down the side of the glass again. You see, all the liquids are of different densities, and that's why they float on each other. The densest, that is the heaviest, is at the bottom, and they get lighter as they go up the glass. Disc number 22, please. Switching to replay. With my special heat eye, this is what a tank of water looks like when one half of it is filled with cold water and the other half is filled with hot. Pull out the partition and look what happens. The multicolored hot water on the left rushes through the cold water on the right and bubbles to the surface. And look at that cold water staying on the bottom because it's so much denser. Whoosh! Now it's all mixing up. The different colours are the various temperatures of the water as they all mix together and finally become the same. Knowing about the density of water is very important when you build a ship. Those lines on the side of the ship tell how deep it's sitting in the water, depending on the saltiness and the temperature. It's called a plimsoll line, after the man who thought the idea up. When you're loading a cargo ship, it's important to know how deep you are in the water so you don't put too much in the hold. Another glass of water, please. This experiment shows how the density of water affects the way things float. Pop the egg in and watch what happens. It sinks like a stone in fresh water, you see? Now take the jug of water and add a lot of salt to it, and be sure to mix it up well. That should do. Into the tumbler with it. Now the egg. And now what will it do? Yes, it floats, because the salt water is denser and is holding it up. Now what will happen if you add fresh water on top? Pour it gently, don't stir it up too much. The egg stays exactly where it was, with dense salty water under it and fresh water on the top of it. An experiment with a very clear result, no doubt about it. Are you ready over there? That jug should do it, and I'll show you a way of controlling the depth at which some things float. Have you got that eyedropper, Leah? In with it, and it floats. The sink plunger on top now. That's right, hold it steady, Leah. Make sure it's airtight, Piers, or it won't work properly. That's it. Now squeeze down really hard, and you're increasing the pressure on the water and altering the buoyancy of the eyedropper. It's going up and down like a little submarine because the water pressure is acting on the air in the little red cap. Here's something strange and very interesting. 5 holes in the bottom of a cap, and of course 5 streams of water. But rub your finger across the bottom and, hey presto, 1 fat stream. It's as if all the little streams wanted to cling together. Do it again and I'll stop everything. The 5 little streams are back again. What do you think that shows? More water, Leah. A spoon and a glass. Now pour. That's it. The water clings to the back of the spoon and jumps through the air to the glass. It's being held together by a sort of skin. Do the same thing on a piece of string. See how the water hangs onto the string as it runs down into the glass? And again, it looks as if it has a skin. It's even clinging to your fingers, Piers. Disc 41, please. If you had any doubt that water has a skin, look at this. A blob of water in space. See how the skin stops the blob breaking up in all directions? And when the astronaut splits it into 2 with a sharp needle, both blobs have a surface skin. And when they join up again, the skin holds the water in the tightest possible shape, in fact, the smallest possible volume. Another jug of water, and bring that pan over, and here's an experiment we can do on Earth. An inch of water into the bottom. Now a piece of blotting paper and a darning needle, and let's see if the skin on the water will support that tiny bar of steel. Are you ready? Right, into the water. And the blotting paper gets wet and sinks, but look, the steel needle is actually floating. It's resting on the surface. Disc 16, please. Switching to replay. Here's a little creature that knows how to use the skin on the surface of the water. It's called a water boatman, and just look at that dent he's making in the water with his feet as he actually walks over the surface on the skin. See? They're not sinking in. Carefully, Surya. You'll need a bit more. See how the skin on the top of the water is holding the water even above the edge of the jug? But dab it with a little bit of soap. And that's it. Skin broken, and that extra water has only one place to go, down the outside of the jug. The skin on water is called surface tension, and you can experiment with it for hours. Float some matches on the water. A drop of detergent in the middle. Bingo! There's a hole in the skin. The matches aren't being pushed away. They're being pulled away by the edges of the skin as they retreat to the side of the pan. You can use that scientific observation to make a boat drive through water. Cut it out carefully with a little notch in the stern. Shape it with your fingers so that it floats. That's right. We'll need water in that tray, Surya. Not too much. That's just right. Boats ready? In with them then. Make sure you've got a little notch at the end. Now each take a matchstick and put a drop of detergent on it. Just one drop on the back end. It breaks the skin, and away it goes, pulled across the surface by the skin as it retreats. Two sheets of glass and some ink, and we're going to make a sandwich, and it could be messy. See what I mean? Be very careful with that ink. Hold the two sheets together and look what happens. The thin gap causes the ink to rise up. That's called capillary action. And it's why blotting paper works, and even why a tree can grow hundreds of feet high and still get fluid to its topmost branches. That experiment's worked very well. My assistant uses capillary action to analyze things. That's a piece of special blotting paper, and they call this technique chromatography. She puts the sample onto the blotting paper through a small hole in the top sheet of the glass. Now it's time to plug the hole with a special container of liquid. Turn the tap on in the small container and the liquid flows out into the blotting paper. You see how the sample in the middle gets drawn by capillary action? After a while, this is what you see and what you can measure. The different colours travel different distances because they're made of different substances. So that's one way to analyse what things are made of. This is brown ink. Look at all the colours that go to make brown. And this is curry powder. And that is the ink from a black felt tip pen. And it's all done by using capillary action and some rather special blotting paper. And here's a useful way to use capillary action at home. Pieces of wool leading from one bowl of water to all your favourite plants. And capillary action will keep them all nicely watered. Try it when you go on holiday for a few days. It really does work. Well, I'm off. Not on holiday, though. I'm going to think up some more experiments for next time. Now, what would they like to investigate, I wonder? Yes, that could be good. Very good. We could very well do that. Most exciting, yes. I just can't wait. Yes, we'll need a pan.
Yes?
Good idea. Heat-proof gloves. Useful when you're cooking.
And do I need the sugar?
Yes, please. We'll need the sugar. That'll do.
And this?
And a saucepan. We're going to make scientific toffee. Delicious. Weigh the sugar, put it in the saucepan, and dissolve it in some milk. Another butter, too. And carefully onto the stove with it, and finally, add something else. Heat. Now look what's happening to all those different ingredients now. They've all changed into something quite delicious. Be careful, it's very hot. If you know what things are made of, there are thousands of different materials that people can make. Disc 35, please. I'll switch myself to replay and show you. Under the microscope, granulated sugar crystals look like this. These are crystals of demerara sugar. Here's some caster sugar. And here they are again at even greater magnification. Guess what this is? It's ordinary salt. This crystal is the sort you find in diamonds. And this one is an emerald crystal. Baking soda? Tin? Copper sulfate? Epsom salts. Look at all those different shapes. You know, you can grow some pretty spectacular crystals with things we've got right here in the kitchen. Fill the glass with water.
I'll get these labels.
I'm glad to see you're keeping records, Sylvia. That's what scientists always do. Now, big spoonfuls of washing soda. Dissolve them in the water and stir it all up. We've got to make a liquid solution so strong it just can't dissolve anymore. Wet a piece of thick white string and put it in the solution.
These?
That's right. It'll give the crystals something to hang on to as they grow.
Still not very hot.
There you go. Right, now put the label on.
No, wait. It goes right under. Right, that's
Right, we'll put the label on.
Now the label. Washing soda, so we don't forget what's in there. Now for the next lot. Copper sulfate from the pharmacy. It's a lovely blue, isn't it? Same as before, as strong a solution as you can possibly make. And hang the wet string in it. Now I can show you what will be happening in those glasses over the next few days. These are crystals actually growing. I've speeded it all up so you can see how they do it. They're taking the material they need to get bigger from the very strong solutions they're growing in. All sorts of shapes and sizes. That's what crystals look like when they're growing. Isn't that pretty? There are crystals in all sorts of things. Split a pencil open if you can. And do you know what that piece of pencil lead is really made of? It's mostly black carbon crystals. And Mummy's very special diamond? Be careful now. Would you believe that it's made out of the very same carbon crystals as the pencil lead was? But there's a big difference, all right, isn't there, Tom? What do you think made the difference? Disc 41, please, Tom. That'll give you a clue. Over to replay. We are deep down inside a volcano. It's so hot the rock has actually melted and it's boiling and bubbling. Diamonds are created in places like this. The crystals of carbon are squashed under tremendous pressures in fantastic heat until they are absolutely cooked. And that can take years and years. When they've cooled down and a jeweler gets to work on them, those carbon crystals end up looking like this. Very precious and very beautiful. This, as you can see, is cut glass. And though it's hard, not as hard as a diamond, of course, it's not a crystal. It's really a liquid. The things aren't always what they seem when you're investigating materials. Look at that glass tube. Even though it's a kind of liquid, my assistant can snap it like a dried twig. But it's easy to understand it's a liquid when you see it like this. a bit like toffee. It's not so easy to see it's a liquid when big slabs of heavy glass are laid out like this. These craftsmen are making a stained glass window, a huge jigsaw of glass shapes, and they're sticking them together with a special glue. This window was made for a cathedral. It'll probably still be there hundreds of years from now. But it won't be the same thickness all the way through. If you ever have the chance to go to a very old church, look carefully at the stained glass windows. You'll find that because glass is really a liquid, over the centuries, the windows have flowed downwards, and that's why an old stained glass window is thicker at the bottom than it is at the top. And sometimes, when they're very old, windows just get tired and they break. Take a wire coat hanger and bend it backwards and forwards for a while. Hard at first, isn't it? But keep going. Something is happening to the molecules inside the wire. Feel it getting hot? And a bit easier to bend now. You're making those molecules do a lot of work. They're starting to jiggle up and down very fast now. That's why the wire is getting hot. In the end, it's all too much for them. Many metals are really quite flexible, but bend anything too much, and the molecules in it just give up. Here's a metal joint that is just in the process of giving up. That grey colour means that it's turning into crystals. It's crystallizing. Here it is under a very high-powered microscope. You can see the crystallized metal, and here's one that's actually broken. Looks as if my assistant is up to something interesting next door. This special machine can measure very accurately what it takes to break the molecules in a material. She's putting in a piece of copper wire and telling the machine to find out how strong it really is. Bit by bit, the wire is being stretched until the molecules just can't hold together anymore. This stuff is really stretchy. It's the material plastic shopping bags you get at the supermarket are made out of, so it's meant to be able to carry very heavy weights. But even the special molecules in this stuff give up when the strain gets too great. Under a special light, these patterns show how the molecules are stretched and squeezed in all directions when they're under strain. A section of railway line, and the molecules are certainly working hard here. And look at this, the stress where two cogwheels mesh. A spanner tightening a nut. The molecules in the spanner are being pushed and pulled in all directions. And the strain round big bolt holes in a metal plate that was used to hold railway lines. That's it. There's a pair of tights in there somewhere, Surya. See how when you stretch them, all the loops that interlock bunch up this way and that way to show you where the stresses are? That's what happens to molecules in materials when they're put under strain. Now, have you got everything ready for the next experiment? Let's find out what happens if you do something to stop the molecules from moving and stretching. An elastic band and a wooden ruler to hold it with, and the sort of cold spray they use in radio repair shops. When you squirt some of the cold spray onto the elastic, it freezes a bit of the band. Now, when you try to stretch it, the frozen molecules just can't move around anymore. They've lost their elasticity. Now my assistant's going to show what happens when you stop molecules moving around when they're trying to. This is liquid nitrogen. It's so cold, it freezes almost anything it touches. Watch what happens when she puts a piece of stretchy rubber hose into it. In a few seconds it will be colder than it is at the North Pole. And what do you think will happen to that squashy rubber? That's a good idea. Goggles to protect your eyes. She's done this before. The squashy rubber breaks like pottery. A mushroom with its molecules frozen solid. Smashes like glass. Now a rock-hard tomato. With all their molecules frozen stiff and locked tight, the grapes can't bend anymore, so they crack apart like little teacups. Now look at this flower from the garden. Amazing, isn't it? Switching to replay. The leaves on the tree are made from the same type of living cells as a flower. If you could look inside the tree, this is what you'd see. Living cells. But when they die and shrivel up, they become a different sort of material. A fibrous material that is very strong indeed. Here's something that came from a tree. Can you guess what it is? Look at those fibers. They look as if they could be very tough, don't they? Have you guessed? They're all microscope pictures of the fibers in a piece of newspaper. Tear up a newspaper into strips like fibers, and this experiment will show you how strong fibers can be. You've got the balloons and some wallpaper paste. So stick the strips of paper over the balloon, first one way and then the other, crisscrossing each other just like fibers. They call this paper mache. It's a messy old job. While you're doing it, have a look at this. These men are using glass fibers to make a boat. They're pressing the glass fiber matting round a boat-shaped mold. Then they soak it with gluey resin, and when it's dry, it comes out just like this, a glass fiber boat. There are lots of them about these days. Right, finished and dry? Now, Tom, all you've got to do is burst the balloon inside. Go on, very good. That's it. The balloon's collapsed, but the paper mache fibers haven't.
Like a hot air balloon.
Reminds me more of an egg. Did you know that eggs are extremely strong? My assistant's got an egg in that stretching machine she was using before. Only this time she set it up so that it's a squashing machine instead. Look at the force on that egg. The numbers are spinning round. But in the end, the machine wins. It always does. The strength of things is often to do with their shape. You can take something quite flimsy and simply by changing its shape, you can make it quite strong. Like that banknote you've got, Tom.
Balance on top of that.
I bet I couldn't.
Do you think that little piece of paper is strong enough to hold up a whole kilo jar of lentils? Yes, it is. Not because the paper itself is strong, it's because the shape of it is strong. Tubes are amongst the strongest shapes we know. Thank you, Pierce. More tubes, eh? What are they?
They're from a cow.
That's right. They're pieces of bone.
From a cow.
When you take some of that marrow out, you'll be able to see the tube shape more easily.
Tubes in. It's a bone. So with this, it looks like...
Look, you can see funny veins sort of thing.
That's it.
It's this shape that makes bones so strong. Pop in disc number 64, please. When things have to be really strong, when people's lives depend on it, very often you find that engineers build them out of tubes. Bridges for one. And do you recognize this? Or this? Something that has to be extra strong and safe. Yes. Bicycles are made out of tubes for that very reason. A piece of stiff cardboard and 4 cardboard tubes. Quite a useful little table.
Ooh, I got my hand stuck. It's very strong.
Legs sticking nicely? I wonder how strong it is.
I'll sit on it. I don't think I'm as heavy as you. Thank you.
Who's going to sit on it?
You try sitting on it. If it breaks, it's your fault. You just get dent in it. Comfortable. And it's also dented. And the legs are going like that.
It holds your weight because of those tubular legs.
Pity those boys don't get to go. What's wrong? You crashed? No.
Well, you've all been busy, haven't you?
Oh, yeah. Can I have my one, please?
The square bridge is yours, Piers?
I'll just have to walk. Mine's first.
Not a very strong shape, I'm afraid. Not much stronger than the cardboard you made it with.
Doesn't like it, does it? Look.
There, you've got a semicircular one. Oh, that's gone too. Tom, you've got a proper arch there.
Very hard to shoot.
Now, I want to show you something. I'm switching to replay. For hundreds of years, people have known that one of the strongest shapes you can have is the arch. The Romans built this. And you can also make very strong things out of the weakest materials. Helicopter blades have to stand up to all kinds of stresses and strains, yet some of them are actually partly made out of a special kind of paper. The special paper is put into a mold and a sheet of carbon fibers placed on top. After it's been baked, the material is then strong enough for helicopter blades. Amazing, isn't it? Ah, everybody here? Lear's scientific sweets have cooled down and they're ready.
Right, who'd like to try some fudge? Me too.
Scientific toffee and a tray full of
I
fudge.
knew you would. You know I know. No peers, don't we? Here we are. It's like glass. It's like the table.
It looks very like glass, doesn't it?
You're going to eat two materials made out of sugar. And they're quite different to each other.
Rock hard as usual.
It's huge. Hold it up to the light. It's thicker in the middle. It feels.
Rather like a sheet of glass, isn't it?
Oh, look. You can see your hands. a toffee hand.
It makes it look.
Yes.
Look at this.
Or something.
Look at the end of this.
Yes, just like shattered glass.
I'm going to have another piece of that.
Oh, greedy guts, you're going to be sick if you eat too much.
No, I won't.
Let's have a look at that fudge. It's crystalline because the sugar was cooked slightly differently. No thanks, Tom. It would wreck my circuits. Never touch the stuff.
No.
Never touches it.
Can't understand what you all see in it, personally. Except, of course, it's quite an interesting material. But then, all materials are interesting, aren't they?